So for today's presentation, titled Calibration Model of the Coteau Embankment at Gardiner Dam, we have with us engineer Vicki, Nguyen, and I'm going to do a little introduction about the presentation. So with support from the Saskatchewan Water Security Agency, KCB has been assessing the potential deformation mechanism associated with the historical displacement measured within the foundation below Gardiner Dam. To investigate the observed response, KCB has developed a 3D deformation model using flat 3D to simulate the ground condition and dam geometry to estimate the dam construction in stages. By comparing the model displacement to the measured data, the material parameters can be calibrated, and then the model can be used to predict the future response of the foundation below the embankment structures. This presentation summarizes the basis methodology and results of the calibration model of the Coteau Embankment at Gardiner Dam. So for this presentation, we have with us engineer Vicki Nguyen. She has 20 years of experience working as a geotechnical engineer in Alberta and British Columbia. After graduating from the University of Waterloo with a bachelor in civil engineering. Over the last 8 years, she has developed numerical models in flat 2D and 3D to assess and design slope stability measurements, perform seismic deformation models, and calibrate model parameters based on field and instrumentation data from tailing facilities, dam structures, and slope stabilization projects. So please join me welcoming Vicki.
Thank you very much. So as mentioned, I'm here today to talk about the calibration model that we developed for the Coteau Embankment at Gardiner Dam. And I'll show you in my next couple slides what that is and where that is. But first, I wanted to introduce the project team that's been helping us put together this very interesting deformation model. So we have our team from KCB, that's myself, Joe Quinn, Kevin Galetta, and Daniel Bertrand. And then we also have the support of the Water Security Agency. So that's the government agency in Saskatchewan that takes care of dams, including Gardiner Dam. And right now we're working with Kevin Matheson and Keisha Hertz. And then on our review board, we've got several people who've been lending their support and giving us some great direction. So we've got Bill Chin, Brian Watts on our internal review board team. And then on our external review board team, we have Dr. Norbert Morgenstern, Mr. Anthony Ratu, and Mr. Stephen Rigby, who's just joined to help us look at the dam risk and structural components. So just a little background on Gardiner Dam and where it's located. It's approximately 100 kilometers southwest of Saskatoon in Saskatchewan, and was constructed in around 1961 to 1964. That's more specifically for the Coteau Embankment portion, and then the main embankment, which I'll show you in a little bit, took a little bit longer to construct, but it remains one of the largest zoned earthfall dams in the world, and is also retaining the Diefenbaker Lake, which holds, which is a reservoir that supplies half of Saskatchewan's population. Okay, so looking at the dam itself, the Coteau Creek Embankment is here, the Coteau Abutment is here, and then there's 3 other components of the dam. They include the plateau, the main, and the east abutment. And then underlying the dam, we've got, this is basically a profile along the center line of the dam. So the top of the dam is in brown, and then the top of the clay shale is dark blue, and that includes a slumped zone that lies kind of near the center of the Coteau Creek embankment around here. And this is just showing in a little bit more detail where that slumped region is. So if we're looking from a top-down view, these are aerial photos that were taken the late 1950s before the dam was constructed, but you can see the extents of those slumped zones into what was previously the Coteau Creek. And there also exists some of these slump zones along the east abutment, but we'll be focusing our attention on the Coteau Embankment for today's presentation. Okay, so on this next slide, just showing the type of challenges that they encountered when they were constructing this dam. You can see a pretty clear shear zone that they excavated through the clay shale. And based on back analyses that they completed at that time, based on the deformations that they were observing, they were estimating strengths as low as 5 degrees, which seemed extremely low at that time, especially looking at the laboratory testing that had been completed. But through kind of observation and looking at the performance of the dam, that's the type of strength that they were looking at. And you can see in this diagram below just where the shear zone is located. So essentially there's the slump debris that has moved along the top of the intact shale. And in this boundary between the slump material and the intact shale, this shear zone has developed. Okay, so looking at the historical performance of the dam, this was prepared by Jasper and Peters in 1979, but you can see from this line up here, this is the pore water pressure response below the crest of the embankment. So during construction, you had excess pore pressure developing due to construction, and then you can see for the next 20 or 30 years, that pore pressure has remained high, and at some instruments, it remains high to this day. So that's one of the things that is contributing to the large displacements that were observed during construction and the ongoing displacements that have been observed during operation. So this line represents the crest of the dam. So you can see as material was placed, the pore pressure responded, as well as the displacements from SIs downstream of the crest. And at the end of construction, they had a total displacement of around 0.8 meters downstream. But after they were finished construction, those displacements continued to accumulate. And that's one of the things that our deformation model is looking at, why those deformations are continuing to occur, and how long do we expect them to occur, and are there any consequences associated with that? So you can see during this time period, there's still some displacements occurring, even though the end of construction has been reached and there's no reservoir loading applied. So that's just constant loading during this time period. And then as the reservoir loading is applied, this line is representing the reservoir. You can see that additional displacements are occurring. And on this next slide, you can see it in a little bit more detail. So this black line represents the reservoir elevation. And then you can see it's a little bit subtle, but each time the reservoir is raised, we get a small amount of increased displacement, around 2 millimeters per cycle. It's a little bit more clear in this blue instrument that's located just downstream of the crest. And then when the reservoir comes back down, you can see that the displacements remain constant. So each cycle, they get incrementally more displacement, and it doesn't return back. So that's why they're just getting additional displacement each time. Okay, so going into our analysis methodology. So in speaking with our review board, there were a couple tenets that we really wanted to hold true in the analysis that we're doing. Number one, our objective was to achieve a model equivalence. So what that means is that you're honoring the data, you're taking all of the different pieces of information that you have. And luckily for us, in this case, we have a lot of information because they have data that they collected since the beginning of construction all the way from 1960 until now. They've maintained all of those, not all of the instruments, but a lot of the key instruments they've maintained. So we want to take into account all of the data that was collected during that time. We also want to look at all of the laboratory data that was collected. So that represents our reasonable physics, that all of the components that we're adding into this deformation model are founded in reality. They're based on laboratory test results. And then once you combine all of these different aspects, the geometry, the physics, and the results, then you can feel confidence that your model is representative of what's actually going on in reality, that you've come up with an equivalent model. Because of course you can't have something that's exactly what's happening in the ground. We don't have that much information, but with so many different variables, you don't want to just complete basically a numerical exercise where you find a couple of variables that give you the right answer. You want to say, okay, I'm using this number. I'm using that number because it's supported by the laboratory test data. And when we put it in the model, we get a response that's similar to what we're seeing in the performance of the dam. So that's the main methodology that we followed when putting this together, looking at the results, the geometry, and the physics. And I'll describe each of those parts as we go forward in this presentation. So the next thing that I wanted to talk about were the potential deformation mechanisms. So again, at the beginning of this project, we basically tried to think of all of the different potential mechanisms that may be affecting the deformation that we've been seeing ongoing at Gardiner Dam. So they include time-dependent displacements. That's something akin to creep displacement. So under constant loading, you're continuing to move. And then some other potential mechanisms that have been identified by others are the progression of the saturation front. So this was put together by Jody Scammell in his thesis, and it talks about how because of the low permeability, of the shale, the excess pore pressures are very slowly dissipating, and as they dissipate, that results in continual consolidation of the material, and that's leading to the incremental movements that we're seeing each cycle. There's also cyclic softening. So that idea is that every time the material is loaded and unloaded, the stiffness decreases slightly. And then that means that the next time it's loaded, it's slightly softer and can move a little bit more under the same amount of load. And the last mechanism that we looked at was pore fluid chemistry. So that's a reduction in the shear strength due to changes in the pore fluid chemistry. So as the salinity in the pore fluid decreases, then the strength proportionally also decreases, leading to potential more displacements. So in our project, what we did was we developed laboratory tests and then also tested this in our model to see which of these components could potentially affect the response of the model. And then we also looked at taking the models step by step. So we started with all the things that we knew. So that, for example, that's the geology based on borehole data, historical laboratory tests, construction records, and we built this model and let it run once to see how close we were to the results. And then if we saw that we weren't there, just started to layer on the complexity. So we weren't trying to bring all the elements in at once. We wanted to bring in each one piece by piece to see how they would affect the results and how significant they could affect the results. So firstly, I'll just talk about how we constructed the model. So that involved looking at the model geometry, the stratigraphy, the performance data review, and model parameters. So first, for the model geometry, there was, seems quite simple, but there's a huge amount of effort that went into this because we have a lot of data going back from 1960, but a lot of that data is in physical copies. So WSA gave us a whole bunch of drawings, and then we went through them and started to digitize them and put them in a format that we could bring into our deformation model. So this is just showing the a cross-section again through the center line of the dam, but it's showing the different contracts that were completed as part of the construction of the dam. And by incorporating each of these construction surfaces, we were able to represent how the dam was constructed, not just in terms of height, but in a 3D sense. For example, in the main dam, they constructed the east and west abutment first, and then constructed the center later. So when you're looking at the displacements, first, they're going to be directed towards the center, and then as you fill up the center of the dam, they start to progress downstream. So we're trying to capture those effects. Okay, so this is another drawing just showing the different construction stages that we incorporated into our FLAC model. And then these were a little bit more challenging, but they were basically survey or topography plans that were hand-drawn. And then we went in and digitized all of those individual contour lines and developed a civil 3D model from that. Okay, and then of course, again, trying to honor the data. So when we developed our slip surface extents, we looked at our SIs and identified the area where the shear was taking place. And then using all of those discrete points, we developed a surface that's representative of the shear zone. So that's representative of the elevation, and then it also represents the top and bottom elevation of that shear zone, whether it was a plane at a certain location or displacement over a thicker region. Okay, and then looking at the stratigraphy, so that again, part of that was internal zonation, so looking at the as-built drawings for the dam and developing surfaces for that. And then from the foundation geology, we had these borehole logs, and from that we delineated the different shale units, the overburden, and the fill for our different surfaces. In terms of our performance review, so the objective for this was to look at all the data we have available. One of those is a wealth of piezometric data from different piezometers. So what we did with that was we took all those discrete piezometric data points, and then we interpolated those results to come up with our pore pressure distribution in the model. So instead of assuming a water table or a B-bar or an RU, instead we're taking the piezometric data directly and applying that into the model, just to take into account the spatial variation. And then also we wouldn't have to do a coupled analysis with seepage and permeability and that type of thing. We're just taking the pore pressures directly and inputting them in the model. So any kind of pore pressure change or response is automatically accounted for in the model. And then to evaluate the performance of our model, we looked at calibration to different displacement measurements. So that mainly what we're looking at are the SIs, but we also looked at the settlement gauges, and they also had movement lines. So that's pins that are installed along the surface of the dam. And then that was surveyed post-construction. And then we saw if the surface of our model was moving in a consistent fashion with those movement lines. So if we're able to match all of these different instruments, the direction, the timing, the magnitude of all these displacement measurements, then we can feel more confident that our model is reaching that model equivalence. Oh, yeah. Okay, so for the performance data review, this is just showing all of the different piezometers that we had. Blue indicates that we didn't have any data at those points yet, and then the colored ones indicate the B-bar that was measured at that location. And then what we did was, you can see the interpolation that's taking place. So the upper figure is showing what the pore pressure was earlier on during construction, and then as the dam was raised, you can see the dam's a little bit higher in this lower picture, then the pore pressure is increased accordingly to match each of these little circles, which represent the piezometric reading at each of those points. In terms of the SI readings, it doesn't seem like it would be something that's complicated, but again, because all of this was paper-based at that time, what we had to do was digitize the results from each of them, and then take the azimuth for the SI, and then take the components so that we've got our displacements and the X and Y coordinates consistent with our model. So just a little bit of work and a little bit of math to have everything in a consistent coordinate system so that we could compare the results. And then once we put that all together, this is a sample of the results that we had. So the red line is representing the response from FLAC, and then the blue line is representing the result, measured response from the SI. This one's a little short because sometimes when they were measuring it before, they were only measuring the displacement along the shear zone, but you can see we're generally matching the direction and the magnitude from the inclinometer profile. And then when we look at the cumulative displacement plot along the shear zone, again, we're generally matching that magnitude and timing of those displacements as the reservoir, or sorry, as the dam is constructed and then the reservoir is raised and lowered. And then on this plot here, you can see the direction of the red again is the FLAC displacement vector, and then the blue is the measured displacement. Okay. And then the last thing that went into the model were the parameters. So there's quite a bit of work that went into this, but it included looking at model parameters that had been developed by others. So we incorporated that into our model, including a deformation model developed by Morgenstern and Simmons in 1980. And then we also calibrated our material parameters based on our laboratory tests. So that's taking an element test. If you don't know what that is, you take an element in FLAC, and then you run your laboratory test on, or you simulate your laboratory test on it, and you apply all the material parameters that you think are appropriate. And then you see if the result, your simulated lab test gives the same result as your physical lab test. And then you can feel, again, more confident that you come up with parameters that are reasonable and representative of that material behavior. And then the last thing that we included for these model parameters is the reservoir loading. So based on the deformation mechanisms that we that I mentioned before, there's potentially a time component to the response of the foundation and the performance. So what we wanted to do was take the reservoir loading as it's been recorded and apply that into the model. So our model also has a time component, and then we're raising and lowering the reservoir at the same rate that was based on their records. Okay, so just looking at some of the sampling and testing that we did. There was a lot of previous laboratory testing that was completed, but we also went and did our own program, and that included collecting block samples, drilling boreholes, and then one of the newer tests or more advanced tests that we completed as part of this project was looking at the creep response of the material, and then also the cyclic response. So this is the triaxial testing that was completed, and then this is representing the clay shale sample that we're using. So because we weren't able to target the shear zone exactly, we manufactured our own shear zone and then put that back in the in the testing apparatus to see what results we're getting from that. So again, we're taking all of these initial material parameters, and then we're bringing them into our deformation model through our laboratory data calibration to the triaxial results, constant load creep test, and also our cyclic triaxial. And you can see here, there's not a lot of details in this presentation due to time, but we're hoping to present some of these in future talks that go a little bit more into exactly the lab data that we had and how we made these fit, because there's quite a bit of work to make it work. But this is just showing getting our hyperbolic parameters to match our triaxial tests, and then Berger's more parameters for a constant load creep test. And then lastly, the cyclic triaxial test, just looking at what type of function would give us the progressive decrease in stiffness for each loading cycle. And this is showing what I mentioned before, where we applied the reservoir in stages, and we applied it as it was recorded. So for each stage basically represents a raising or lowering of the dam. And then during that stage, we're applying the reservoir in the rate that it was applied. And then just looking at the model, this is kind of a graphic to show what the model looks like and where the reservoir loading was applied in comparison to this aerial photo. So that was the process of putting together the whole model, and then we started our main calibration process. So we already had the material parameters from our laboratory data calibration, but those are just discrete data points. So when we're calibrating it to the performance, we want to be within the range of the laboratory data, but also take into account some potential spatial variation or differences in the performance in the lab kind of bench scale versus the macro scale in the field. So that included calibration to the slope inclinometers, settlement gauges, and the movement lines. So you can see on this plot, this is the spatial variation of the material strengths, specifically along the shear zone that we came up with. So near the crest, we have a lower strength zone of 5 degrees, and then it increases to 7 degrees. And then along the abutment, it increases a lot, again, to 12 degrees. And we validated those strengths by looking at the performance data, and then also looking at the geology that was present in those locations. So in the next slide, I'm just going to show an example of the different comparisons that we did. So for this one, this is the settlement gauge results, and that's going to help us evaluate the stiffness parameters mainly that we selected, and see if they're leading to similar vertical deformations as what we're getting in the model. So again, the red line represents the FLAC results, and the blue line represents the measured results. So generally matching for those two elements. And then the next one I have is the movement line. So this one, we've got the movement line here, this purple line, and during the years, they surveyed the data by looking at these even movement lines and then measuring the downstream displacement. So that's what's represented by this plot on the top. And then they also measured the elevation change or settlement. So that's represented by this lower plot. So generally these movement lines, because they're just pins sticking out of the ground, usually the accuracy of them is a bit lower, but they can still show you the general trends of displacement, where you're getting more displacement versus less displacement. And we were finding what was interesting is that the majority of our calibration efforts were focused on calibrating to the SIs. And we basically just looked at these movement lines at the end as kind of a secondary validation. So we're pleasantly, we're happy to see that they're generally matching, even though we weren't specifically trying to calibrate to these results. So that just, again, gave us more confidence that we're moving towards that model equivalence, and that the aspects of our model that we're putting together are generally consistent or representative with the behavior or the mechanisms that are present in the foundation. Okay. And then on these next couple of slides, so I'm going to show the response at a couple of different representative SIs. So this one is just downstream of the crest. And again, you can see when comparing the blue and the red line, maybe a little bit small, but I think you should be able to see it, that we're generally matching the magnitude and direction of those displacements. You can also see that from the inclinometer profile, that the direction and magnitude are similar over the same time period. And then looking at the cumulative displacement plot, again, we're matching, this first part is showing the displacement at the end of construction. And then we zeroed the displacements and compared again following construction. So by incorporating each of those different deformation mechanisms, and I'll explain that in a couple of slides, how we did that, we were able to match all of these different aspects of the performance that's been observed. So that's for this instrument just upstream. And then this next one is a little bit further downstream, but still matching relatively well. And then further again downstream, still matching. So we're matching not just one instrument, but several instruments in different areas spatially, and getting a relatively reasonable result. And then our last example is from the Coteau Embankment. So again, matching the displacement, magnitude, timing, and direction. Okay, so on my next slide, I've just got those same deformation mechanisms that I mentioned earlier. So, and then next to it, it's just got some information on how they were incorporated into the model. So as I mentioned previously, we tried to build this model in layers of increasing complexity. So the first thing that we did was develop the model and then just incorporate the measured pore pressure response. So I think that one is pretty representative of this gradual dissipation of the pore pressures. So it's something that was already included in the model, but we found when we ran it with that, it wasn't able to capture all of the deformations that have been observed. But I think it's one of the kind of underlying responses or mechanisms that's affecting the underlying response, but it wasn't able to give us that progressive increase of displacement each reservoir cycle. So based on that, we looked at cyclic softening. So that was evaluated using our cyclic triaxial results. And we found from that we got quite a good trend. It was showing more softening during the first couple of cycles and then progressively less. So that kind of matches the behavior that we've been seeing with displacements slowly attenuating with time. So we incorporated that into our model, but again, it gave us a little bit more displacement, but not enough to capture all of the displacement that's been observed during the last 60 years. So the next component that we incorporated was the time-dependent displacements. So that's incorporating the potential creep response of the material. And that's something, if you remember from near the beginning, that was observed because at the end of construction and then before reservoir loading was applied, there were some displacements that occurred over the span of, I think it would be 2 years. So those are associated with our time-dependent or creep response. And we found when we incorporated all 3 of these different deformation mechanisms, now we're able to capture the displacements that have been observed, and we were able to get those matches to the settlement gauges, the SIs, and the movement lines. And then the last mechanism that we had been considering was the pore fluid chemistry. So that's as the seepage front progresses, the material progressively gets weaker. But when we did some of our initial seepage analyses, we found that because the shale was so impermeable and in some areas, the pore, especially the critical areas, the pore pressure, excess pore pressure was remaining high for so long that probably a lot of this movement of the seepage front hadn't occurred yet and wouldn't likely be a big contributor to the displacements that have been observed so far, although it could become an important deformation mechanism in the future. So it's something that we can still look at for future predictions of the model, but it's not something we found we needed to incorporate in the model at this time. Okay, so just in summary for our model validation, we feel that at this point in time, we've reached the model equivalence by staying true to those 3 tenets that I mentioned at the beginning and honoring all of the wealth of data that has been provided to us by WSA and other people who have been working on this project. So again, we developed a 3D model that incorporated all of the geometry elements and construction sequencing involved in the project. And then we also looked at material parameters from the laboratory testing, from historical characterization to incorporate all of that into our model. And then we calibrated, took that model and did our final calibration. So looking at the potential spatial variation or time-dependent effects that wouldn't be able to be captured with laboratory testing or other previous characterizations that had been completed to try to match the displacements throughout the years. And we feel that at this point in time, we've reached fairly good calibration. We're matching on a lot of the different metrics that we were trying to, and we're expecting that although we could probably spend years continuing to calibrate, we'd be kind of just sharpening the pencil and not really gaining additional value out of the model from what we have at this point. So now that we've reached that model equivalence, the last step is to use this model to predict the future response of the dam. So that's going to help WSA evaluate, complete their risk assessment and look at future ways that they want to operate the structure. So some things that we're looking at are what will happen to the dam if they follow operation as is right now, and then also what could potentially be the response of the dam if there's changes in the loading parameters. So to support that, the things that we're looking at this time are, again, just running the model for the next 50 or 100 years to see how much additional displacement we're expecting to get, and if those additional displacements could have an impact on the stability of the structure. And then also looking at potential changes to the loading rates, either different needs that they have in terms of the water, the reservoir that's in Diefenbaker Lake, or potential changes due to climate change effects, if that's going to increase their need for water or decrease the amount of water available. All of those things could potentially affect the operation of the dam, and something that we can look at. And then also extreme weather or flooding events, just like the flood that we had in Calgary in 2013. That watershed is actually connected to Gardiner Dam. So we had the flood in Calgary, and I think maybe 5 days later, the water made its way to Saskatoon and Saskatchewan. So luckily they knew that it was coming, and they could operate the spillway to mitigate the impacts. But yeah, it just keeps in mind the importance of looking at these different risk measures and making sure that we're accounting for them and preparing ourselves. And then another piece that we're looking at is just investigating the impact of these future displacements on the structural components of the dam. So in total, I think there's been around 2 meters of displacement at Coteau Dam and almost 3 meters of displacement at the main and east dam. So quite a bit of displacement that's occurred already, but still all the structures are still remaining operational, which is great. And we just want to make sure that we're able to help them and support them continue that operation. Okay, so that's the end of my presentation. Are there any questions?
Hey, thanks to Vicki for the presentation. Now, just raise your hand. I will go with the mic. Okay.
Thank you for that presentation.
Yeah.
I have a couple of questions. One out of curiosity, you talk about 2 meters, 3 meters of information. Was that within the 3D slow strain mode, or did you need to run the large strain mode?
In this deformation model, we just used the small strain mode. Yeah.
So the model is so large that the 2 to 3 meters is a small percentage.
Right. Yeah. I think the model is maybe, I want to say 1 or 2 kilometers wide. Yeah. So it's quite large. Yeah.
And when you were showing the data that you had to digitize, and that looked like a tremendous amount of work probably for digitizing. Can you speak to the balance between the details on the topographic surface, the structure itself, and simplification so that the model doesn't run into numerical instabilities, etc.?
I see. Yeah. I think so when we were looking at that, basically all of our zones or the 3D elements in the model are a certain size. We needed to keep, generally I like to have maybe 1.5 million zones in the model. So if there are elements or aspects to the topography that were more refined than our modeled mesh, then they don't really come into play. So that was one of the things that we used to gauge how much we wanted to look into the data. But also in terms of the construction records, a lot of the time they were just raised this many meters over this many months. So during construction, we didn't have as much data. It's not like what you'd have these days with kind of a full survey of the site every couple of months.
The Crippen model that you use as one of your primary methods or approaches for modeling the deformation, was that a viscous type of model?
Yeah, so that's the Berger's Moore
Yeah.
constitutive model. Yeah, so it has a viscous damper.
Were you able,
Yeah.
and I'm not, perhaps I think I didn't touch that. So were you able to calibrate that to your tests, or was that just an afterthought calibration so that the displacement would be calibrated to the instruments?
Right. So we did a constant load creep test in the lab, and then we ran like a parallel analysis in FLAC using Berger's Moore to match our lab test results using the element test.
Nice. Good.
Yeah.
Thank you.
Thanks. And just to answer your first question a little bit more. So one thing that we did incorporate in the model that I didn't touch on in this presentation is our interface elements along the shear zone. So those are kind of 2D elements that allow the model to move freely along that interface. So that would kind of capture that same like large strain displacement along that shear zone. No problem?
Any other question?
Thanks for the presentation, Vicki. It's really good. I guess it's kind of a question about that shear plane that you guys model. So you said earlier on in your presentation that when they opened it up for the excavations, on that shear plane, that was shear at about 5 degrees.
Mhm.
Did your model, did you guys just input a 5-degree shear plane into your model, or how did you guys model that?
No, so when, again, going back to kind of the simplicity versus complexity, I think our initial estimate of the strength parameter was 7 degrees. So we gave a constant value of 7 degrees to everywhere, but we were finding in some areas we're getting too little displacement, and some areas we're getting too much displacement. So that's why we branched out to the 5, 7, and 12 degree zones.
Just to kind of follow up on that idea, was the shear plane that they found out there, is it just an extremely slick inside the plane that sheared so much, or is it analytic, or because you guys did the pre-shear clay tests from your lab testing data that you showed there?
Yeah.
Were you guys able to match something similar with those tests to compare those?
I think probably in the actual shear zone, there's a little bit more bentonite, like the plasticity is quite high, but when we were doing our laboratory tests, we collected all of our samples and then we did Atterbergs on all of them to find the ones with the highest plasticity to do these tests on, to get it a bit closer. But I think along that boundary between the slump shale and the intact shale, there is that layer of bentonite that's that has a very low strength, and generally you're finding these in different clay shale materials, that thin layer that likes to slide.
Thanks so much.
Yeah.
Do you have a question?
So first question from the people on Zoom is, have the results of your work indicated a need of additional instrumentation and monitoring?
So that's actually part of our next phase of tasks that we'll be completing for this project, just evaluating all the existing instruments and then potentially recommending the installation of new instruments based on our model results if they identify other key areas that we might want to take a look at and monitor. So that's something that will be forthcoming.
Any question here? Okay, next question. I'm curious about your approach on modeling the reducing in strength with time from 12 degrees to 7 and then 5, considering the variation in saturation from and fluid chemistry to estimate future deformation.
Okay, so in our model, we don't actually change the strength with time. So we've got the 5 degree, 7 degree, and 12 degree, and they remain at those strengths throughout the model. And then what's causing the continued displacement is more associated with the change in stiffness and then also the creep parameters that we've considered.
Next question is, has there been any damage sustained to the spillway or other concrete structures?
There hasn't been any significant damage to the spillway at this time. It's part of the ongoing review that we're doing, the structural review, but there's nothing significant yet. Yes. Or sorry.
We should be coming in person.
Usually they're still doing the like this.
My understanding is that
But
They
it was
still-
still in the early stages, right? There was not a lot of movement by structure, or has that been something that helped you to calibrate for?
it's something that we're looking at for comparison, but it wasn't specifically used for the calibration because the values were quite low. Yeah. More helping us look for kind of red zones that we'll want to look into further.
So thank you very much, Vicki, for your presentation today. Yeah, there is a lot of extra work that you can present in the modeling part.
Yeah.
So you are very welcome again. Anytime. And thanks everyone for coming. Next week, we are going to have Dr. Asil Abu-Dib presenting on CPT testing in a few oil sand projects, including evaluation of liquefaction potential, characterization of tailings, and monitoring of compact effort. So thank you very much for coming.